coming. Let's start. I have a lot of slides, so I want to start on time. Thank you very much. Well, thank you for coming. My name is Yassin Asri, and I am a Java software lead. I'm going to tell a little bit more about me in the coming slides. But today I'm going to tell you about quantum computer, what it is, what is the dynamic behind it, and I will give you also a small introduction how you can write Java quantum computer languages. So this is about me. I hold a bachelor degree in physics. That was in 1996 from my hometown in Morocco, where I'm originally from. In 1997, I moved to the Netherlands, and I decided to study something else, which was software engineering. And in 2004, I got my master's degree. And now, 20 years later, I serve as a Java chapter lead at ABN AMRO. Anyone here with the physics background? All right, I'm safe, so that's good. So if I forget something, please complete me. Let me tell you a story you may already heard of, which is the story of the king and the chess inventor. So back in the days, a king was really happy with the chess game, and he decided to reward the chess inventor. So he asked him to name anything, and he would promise to realize it for him. So the smart inventor asked to place 1 grain of rice in the first tile, 2 on the second one, 4 on the third one, 8 on the fourth one, and so on. You get the idea. The king, of course, laughed at him because he wants rice instead of gold or money, and he thought that would be an easy task, and he said, okay, come back next week and I will realize it for you. When the king started putting the grain of rice on the tiles, he realized that on the 64th tile, he should put this number of grain, and that's a number that's bigger than what his kingdom can produce in many, many years. How the story goes? Well, there are 2 versions. The first one is that the king killed the inventor because he was mocking of him. And the second one is that he made him king instead of him because he couldn't keep his promise. But of course, I tend to believe version number 1. What is the moral of the story? Never joke with a king. And the second one is this story shows the potential of and the power of exponential growth. This is the map of physics, which is a roadmap of our understanding of the universe. It shows us how the universe interacts and behaves, and it includes fields like classical physics, relativity, quantum physics. But in my opinion, it has a really important part, which is philosophy. And I can imagine that our ancestors, or even the first human being on this planet, asking themselves questions like, what is the nature of reality? How come? Do we have a free will? What are the building blocks of the universe? And through the years and recurring civilization, we could answer, and we are still trying to answer some of these questions. Isaac Newton, for instance, was able to explain gravity. He came up with lots of motions, and he even invented calculus for this. James Maxwell was able to explain electromagnetism, and he came with his famous equations for that. We had thermodynamics for heat and energy transfer. We had optics. So everyone was happy until they started to look at teeny tiny particles like an atom of an electron, when they realized that these sets of physics and these laws does not apply for them, and it gives wrong answers. And the new sets of physics was then necessary to explain the behavior of microscopic particles like, again, an atom or an electron. And that's quantum physics. You can make the link, if you hear the term quantum computing, then think about computing which is done based on a quantum, like an electron or a photon or even smaller than that. Don't get fooled by the term classical in classical physics. It's just a terminology that quantum physicists give to this, because this law couldn't explain some kind of behavior. But if we want to launch a rocket in the sky, for example, we still need the law of motions of Isaac Newton. I mean, this presentation is made possible because we have the electromagnetisms applicable, for example, in Wi-Fi and so on. So quantum mechanics, 1920s was the birth of quantum mechanics, and quantum, if you translate it from Latin, it literally says how much, quantity, an amount. And it's a world based on probabilities and certainty. So in classical physics, you can predict the movement of an object. You know the speed, you know the velocity, you can know everything, but not in quantum physics. So if you want to look at the behavior of atoms, then you cannot find a position with certainty, or the momentum with certainty. So it's like chance, 50-50 or whatever it's applicable there. And it's a strange world what's going on there, because you see particles popping in and out of existence. You try to measure them, but they are not there anymore. But you know they were there a second ago. Richard Feynman, one of the brains behind thermodynamic and behind quantum dynamics, said once, and I quote, "I think I can safely say that nobody understands quantum mechanics." So it says a lot about the complexity of this world. Personally, one of my favorite equation is this one, which is the Schrödinger wave equation. So you can, one other strange part about quantum is that it leads dual lives, double life. So it can be a particle and a wave at the same time. And this is the wave function of it. And if you look a little bit closer, you will find an imaginary number in it. Of course, I'm not going to go through the math, but an imaginary number, the square root of I, is a negative number, which in reality does not exist. So you think about it a little bit, because our brain, for instance, is made of atoms and quantums, right? And we try sometimes to solve problems, but we forget sometimes that we are the problem itself, because we have an imaginary number in our world which governs our behavior. But there are two properties of a quantum which are relevant for the quantum computer. I will also only limit to two. We have a superposition and entanglement. I'll start with superposition. The ability of a quantum system to be in multiple states at the same time until it's measured. The best way how to explain this is using the Schrödinger's cat paradigms. Personally, I think if I have a cat, I will call it Schrödinger, just to honor Erwin Schrödinger, of course. But you take a cat, you put it in a box, you seal it, then you don't know what is the state of the cat. Is it dead or alive or jumping or playing, whatever it is, you don't know. In fact, the cat is in all possible states that you can imagine. But let's only focus on two states, which is dead and alive. So if you don't open the cat, if you don't open the box, don't open the cat, please open the box. If you don't open the box and you don't look and you measure, then you don't know in which states the cat is. But as long as the box is open, then the cat dead and alive at the same time. So, and it's important to notice here. So you can write this quantum state of the cat like as a mathematical formula, which is quantum state is A cat 0 plus B cat 1. And this is a direct notation of how you write quantum states. And cat comes from brackets, the word bracket, where A square is the probability of the cat being dead, for example, and B square is the probability of the cat being alive. That's superposition. From the other hand, we have entanglement. And entanglement means two particles remain connected even when separated by vast distances. You can see also a particle as a sphere. It has in a three-dimensional space as a sphere. And for example, the particle has a electromagnetic field. So it means that we have some kind of pointers like what we have for our Earth. It has an electromagnetic field. So you can see it as a square. And this electromagnetic field is pointing, for example, to multiple directions at the same time. Remember the superposition? Every state is possible. So it's pointing to some kind of state, and then in three-dimensional space. And then if two particles are entangled and you look at one, the other one will also reveal itself as the same state as the first one. So if the first one is pointing to south, the other one will also point to south. Nobody understands how it works, but it is like it is. And I remember Albert Einstein called this spooky action on distance. Enough about quantum mechanics. Let's talk about quantum computer history. And what we know so far is that the Greek, 200 BC, invented some kind of machine to simulate the world. It consists of some disk you can rotate. And the idea is to simulate the movement of our solar system. So we have the sun, the moon, and so on. And then we had to wait until the year 40s of the last century, when the Second World War broke, and Alan Turing decided to create, who was, by the way, a mathematician, who decided to create a machine to crack the German one. And so far, this is the first digital computer, what we know. And of course, in the 1960s, we have literally computers the size of this room. And of course, the inventions of transistors and the evolution of technology made possible that the chips get smaller and smaller. And then in the 90s, we had, the 80s, we had our personal computers. And then nowadays, we have computers everywhere, CPUs even in our hand, or even smaller devices. I think you can guess that the next generation of computer would be the quantum one. Now, to understand how quantum computer works, it's important to understand how CPU works, the current CPU. So a CPU is consists of a collection of transistors, and transistor is made of semiconductors, of course, from silicon atoms, for instance. And a transistor is a switch. So if the switch is on, we have flow of electricity. If the switch is off, no current of electricity. So with transistor, we can manage or control the flow of electricity. And of course, if we talk about transistors, it's really important to talk then about Moore's law. And Moore's law is not a physical law, but it's a law based on some kind of observations. You can see it as follows. So the number of transistors in an integration circuit doubles every 2 years. And you can imagine a Word document, and this Word document, you write the word transistor, right? And you write it with certain font, like, for example, 40. 2 years later, your technology becomes much more better, and then you reduce the size of the font from 40 to 20, and now you can place more word transistors in your page. And for the CPU, it means that more transistors means more calculation capacity, of course. If you look at this table here, which shows the evolution of this, so in 1968, we start with 20 micrometer, and now we are operating even into nanometer. That's really small, really. I mean, even the size of the COVID virus vary from 50 to 150 nanometer. And then, yeah, we managed to create a transistor which is smaller than the size of a virus. And I suppose this will go on, and we still have smaller transistors, but this will bring some problems with it. 2 problems. The first one is heat. So when the transistor becomes very, very small, consists of few atoms, then heat becomes a problem, and then your circuit will just melt. And the second one, which is also a quantum property of an electron, which is called tunneling, if I remember. So the electron will jump from one place to another, even if the circuit or this switch is off. So it means that the transistor will be useless. So it means that Moore's law will come to an end, of course. Quantum computer. So the idea of the quantum computer comes from Richard Feynman in 1982. You remember the guy who said nobody understands quantum mechanics? So the idea is coming from him. And it's based on behavior of atoms and electrons. So we see in the transistors, it contains of atoms, a lot of atoms. So why don't we use just a single atom or electron, for example, as a central processing unit for this? It will be the ultimate computer, so there will be no evolution of the computer after that, because it's based on the smaller things, object, what we have in our building block. And of course, it takes its power from the quantum mechanics and properties like superposition and entanglement. To understand how it works, it's good to do some comparison between a bit and a qubit. And a qubit stands for quantum bit, and that's the equivalent bit in the quantum computer. So a bit, as we saw, is binary. It's a switch. It's either 0 or 1. A qubit is different. Superposition, it can be in the multiple stage in the same time. So it could be 0 and 1 at the same time. That's really important to note and understand. You can imagine it's like you flip a coin in the air, and while it is in the air, then you don't know in which state the coin is. Is it tail or head? You don't know. It's a tail and head at the same time, right? Only if you take it in your hand and you measure it, then it reveals itself as the head or tail, but not as long as it is in the superposition state, then you don't know. There are some chances. What does this mean? Now, let's take, for example, a system with 1 qubit. 1 qubit can be, if a qubit is in a superposition state, then it holds 2 states, 0 and 1 at the same time. So if I want to match it in the classical world, then I need 2 bits, right? 2 transistors. If I have 2 qubits, then I need 4. 3, I need 8 transistors because 0, 0, 0, 0, sorry, 0, 0, 1, 0, 1, and 0, 1, so that 8 states, and then I need 8 transistors. Now, if I go to 64, for example, I need this number of transistors, and I can guarantee you that all manufacturers in the world will not be able to produce this number of transistors in many, many years. I think now you can make the link between this and the story with the king and the chess player, right? Here, the qubit adds another dimension to calculation. You can imagine it as if you want to travel, you have a horse or a plane. Of course, with a plane you can fly, which a horse cannot do. And we are talking about supremacy here. I mean, qubit is really supreme. You cannot compare the qubit with the bit and with the transistor. It adds really more infinite power to calculation, as we are going to see later on. To understand a bit more, let's take some examples. And one of the examples is, imagine that you have a safe. And for sake of simplicity, we have a safe which consists of 4 digits. And it's binary. It's either 0, 0, 0, 0, 0 or 0, 1. So as a person, if I want to open the safe, then I have to try 16 times. Try the first one, doesn't work, the second one, and so on. Maximum 16 times. If I have this computer, and I know how the AND logical gate works, then I would do it in 4 times. Because you can apply this AND logical gate, and then you only need 4 times. But if I have a 4 qubits, a system of 4 qubits, then I only need to try once, and that's it. So, for example, the first qubit will have 0 and 1 at the same time, second one similarly, and so on. So my quantum states would be something like this. A, 0, 0, 0, where A is A squared, the probability of this being in this state, and so on. And one of them, of course, is the right answer. So you can imagine if I have a safe with thousands of, a password consists of thousands of bits, yeah, with this computer, I need to try many times. Depends, of course, the length of the secret. But in quantum, with a quantum computer, I only need to try once. Another example is this maze. For example, with the classical computer, I need to try every possible path. So if I come to the dead end, then I should come back and then try the next one. Not with quantum computer, because quantum computer will try all the possible paths at once. And then you can filter your good answer, of course. And one of the scariest part about quantum computer is this, is security. Our security is based on encryption, how system communicates with each other. And what is actually a public key? A public key is the sum, the product of 2 prime numbers. We take really large prime number, multiply them by each other, and then we have our public key. That's easy, right? But the other way, to defactor the public key, that's a problem. So it takes even our most advanced supercomputers many years to defactor a public key to a private key. Quantum computer promises to solve this in less than a second. So that's really huge. Another comparison is about logical operators. So, for example, for the bits, we have an AND operator, an OR operator, and so on. And an AND operator has an algebraic function, right, which is A multiplied by B. And it will give, we have the truth table, of course, and it gives 1 only if A and B are equals to 1, otherwise it gives 0. One of the logical operators in our CPUs. And so on. So, but it's based on an algebraic function. Mathematically speaking, we can represent 0 by this vector, 1 and 0. And 1 can be represented by 0 and 1. Similarly, we can represent this 1 and 0 by a Ket 0 and 0, 1 by Ket 1. So for us as a developers or Java developers, this is not other than an ordered list. So if I want to create something similar, like this, where it flips the input, so if I say not 0 should be equal to 1, which means that not is equal to this matrix. This is basic linear algebra. Because if I take this matrix and I multiply it by this vector, then if I do simple math, then I will come to this one. Right? So we talk about logical gates in the classic computer. We have an equivalent quantum gates in quantum computer world, and they apply for qubits, right? So if I look at identity, for example, an identity is, it does not change the input. It's if you, I0 is equal to 0, I1 is equal to 1. And this is the equivalent matrix of it. Pauli X gate, and this is what I just mentioned earlier in my previous slide, it flips the input. So 0 becomes 1, and 1 becomes 0, and this is the matrix representation of it. Now things get interesting with Hadamard. A qubit, if you are programming and you declare a qubit has the default value of 0. So it's not directly in the superposition state. And this Hadamard put it in a superposition state with equal chances, 50% being 0 and 50% being 1. So this is what it does through mathematical equation, at least here. But still, if you calculate the probabilities, you will still find 50% chance being 0 and 50% chance being 1. And this is the notation of it. So if you see this in the circuit, you understand this is an Hadamard gate. Another interesting one, which is controlled NOT. And controlled NOT takes 2 qubits. And the first one called the control bit, and the other one is target bit. And so if the first one is equal to 0, then nothing changes. But if the first one, the control bit, is equal to 1, then it flips the second one. So like this, 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. So far, quantum gates. Now, you know how the current computer, what we use, impacted our life, right? In every aspect. The quantum computer will have even a huge impact on our life again. And personally, I think these 4 fields will be impacted: medicina, security, agriculture, and simulation. So in the field medicina, how we make drugs, how we make medicina, is to medicine. In laboratory, we take a lot of tubes, and we put substances there, thousands of them, put substances, and then wait and pray that one of the tubes gives us the right answer, right? We use animals also for experiment. That's because our body and our, let's say, molecules are subjects of a lot of variations. In fact, some of the diseases like Parkinson or cancer are a result of uncontrolled variation. But it's, for the current computer, very difficult to manipulate or to simulate all this variation. It's impossible. But not for quantum computer, because what is the best way to simulate the behavior of an atom than using the atom itself in quantum computer, right? Also in security, I mean, the way how we secure our system is using this prime number. That's not going to work anymore with quantum computer, and security will be a bigger issue, and maybe we should think about different way how security will be managed. Of course, agriculture, because, I mean, look at fertilizers, how fertilizers work. With quantum computer, we can help produce better fertilizers. And of course, simulation, which is a big challenge for the current computer. Where we're standing now, it's a rat race to optimize the quantum computer. It's really a bigger company put a lot of money in them. And I think the first one who is going to optimize this quantum computer will win the race, and then there is a lot of money in the table there. I mean, it's going to manage even or control the world economy even. So Google Sycamore, Google have the Google machine called Sycamore quantum computer has 53 qubits, and they claim, Google, according to Google, that they completed that task in 200 seconds, that a supercomputer needs 10,000 years to finish it. IBM Condor, they have 1,121 qubits, and I must say that if I look at IBM and Google, I see that IBM has a really better ecosystems when it comes to quantum computers. You can log in their platform, and then you can even create some circuits with some drag and drops, and then you can even upload your code, and it will be run by a quantum computer even. Are we going to see more slow again? Because technology gets better and better, and every year we put more qubits in the system. So is this going to be double every 2 years again? We'll see. But it's extremely difficult to create a quantum computer physically, because you need some conditions. And one of the conditions is that the temperature, because qubits should be in a stable state. And we need to make it in a stable state, you need to make the temperature below 270 degrees. So minus 270 degrees. Now the part you're all waiting for, I hope. Java quantum programming. So what do you need to get started? I mean, first you need to look at which type of problems you want to solve. If you want to watch a YouTube video or browse internet, then you don't need a quantum computer, of course. But you should look at the situation. I think the problems where the classical computers cannot perform, then a quantum computer will come to our rescue. You should know or learn a bit about physics because, I mean, as I mentioned, the law of quantum mechanics apply for quantum computer. Mathematics for sure, like linear algebra, like I showed in the example with matrices and vectors. And of course, a computer science as a developer. You should know about quantum gates and circuits. So quantum gates I already explained, so where you can manipulate the quantum bits. And circuits, I'm going to give a demo and then I will explain what is a circuit. You should know a little bit about quantum algorithms, and quantum algorithms are none other than libraries which are already exist. For instance, I already talked about how to crack, let's say, the private key and the public key. In fact, there is an algorithm who already can give you the answer. And this algorithm, I think, is already 30 or 40 years old, which is called the Shor's algorithm. But so far, we didn't have a powerful machine to apply it. But nowadays we have, and then we have a problems with security. So quantum algorithms are a set of libraries provided by the framework that you are using that you can use on the fly. We have Shor's, we have Grover's algorithm for searching a list, for example. We have other things for, I think, for searching databases and so on. You should know, but this is a general concept, which quantum programming languages and frameworks are there. Honestly, for Java, there are not so many. Again, IBM has a really sophisticated ecosystem, but it's Python-based, so not for Java. I hope they will have also a Java version soon. And what's available in the moment, what I know of, there are two libraries, Strange API and JavaQuery. But today, I'm going to talk about Java programming. I want to give a demo using the Strange API. A Strange API is a project, I think the lead developer of this project is Johan Vos, and he wrote a really nice book called Quantum Computing in Action. So if you're interested, you can purchase it. And consists of two parts, high-level programming and low-level programming. And the high-level programming is you don't need knowledge of circuits and gates whatsoever. Excuse me. So as I mentioned, you need to know about these quantum algorithms, which functions are available, and then you can use them. And also consists of low-level programming, and then you need to know the gates, you need to know the qubits, a little bit of physics, and mathematics, of course. and I want to give a demo. Enough talking, right? And first, what I want to show, it's not visible from me from this side, so I'll move. Let's see. So this is Shor's algorithm, so about defactoring two prime numbers. So we have a product, which is this one. Well, first of all, let me show you the POM file. So the POM file includes two libraries, the redfx, which is the strange artifact, and then we have strange fx. This is a visual library how you can see the circuits. I will show you later. So only these two dependencies. Let's go back to Shor, which is this one. And no, I cannot see it from here, Groover. This is this one. Yeah. So this is a simple program to defactor a prime number. A prime number is 21 here. Just one, before I go on, I want to mention something. This library is based on simulator. So it's not, you cannot run it yet on a quantum computer, but it's ready for use. I'll cover that later on. Which means that if it's a simulator, it will work even slower than with your current, if you write this program in your normal Java application. But it will just give you some ideas how this works. So if I have this number and I want to defactor it, then it will show me the result here, which is, I hope it's readable. Excuse me, I really don't see it. Maybe I should come and see this. Stand here. Yeah, so you can see 21 is the factor of 3 and 7. Another example of this is the search. Is this one? Yeah, no, this is the secret. I want to cover it later. Entanglement, Shor's, quantum Hadamard. Yeah, here, this one. Grover algorithm for searching. So suppose I have a list of 8 persons here, and I want to search this list based on some quantum algorithms. That's possible, because there is a quantum algorithm for this one, which is called, it's a Grover, and it's included in this library. So what you do, you construct your database or your list, and then you want to search for this person. And then, of course, in the classical world, you have to iterate over each number, over each entry in the database, but not with this quantum algorithm. This quantum algorithm says that the maximum iterators that you could have is square root of n, where n is the number of the list, the size list. So it reduces to square root of n. And again, if I run it, then it will find my my list. Of course, I run it 10 times, and 10 times it finds the person that I'm looking for. Now, things will get a little bit excited with the low level. And first thing, let's look at the superposition and how we can make the superposition. So this is my program. And I have a quantum execution environment. And if you look at this one, this quantum execution environment, this is an interface, right? This is an interface. And in this interface, this is my implementing class, right? And this implementing class is used for simulation. Unfortunately, we don't have a cloud quantum computer yet, but maybe in the evolution of this library, we will have one. And then what you need to do then is just change this one, and then your program will still work in a quantum computer. So we defined some kind of steps to create our circuit. And here, so I define my steps, and in my step here, I add a gate. You remember this gate? And I add a Hadamard gate. And I apply it to the first qubit. So I have only one qubit. And then I put it in of course, if I put it in a qubit, sorry, if I put this qubit in a Hadamard state, so it will be in a superposition. Remember, superpositions means that if I measure it, I have 50% chance to be 0 and 50% chance to be 1. Well, let's look at this. Okay, so these are some probabilities. Cubit with probability 1 is almost 50%, 0.4999. Measured it gives 1. But there is also this FX library with it, which shows this user interface. So I have a qubit, first qubit, state 0. I put Hadamard gate on it, and then I have 50% chance for 0 and 50% chance for 1. If I run this thousands of times, this is what I did here. So I run it, show probability of this program. If I run it thousands of times, I will have almost 500 times to be 0, and almost 500 times to be 1 here. So it's 520 and maybe 480 here. So this is the Hadamard gate. Now let's go a little bit to show how entanglement works. We can create this entanglement with our computer. And you can see here, if I measure, for example, let's first walk through this is really not handy, I'm standing here. But anyways, so this is our quantum environment. Again, we create a program, and now we have 2 qubits, the first one and the second one. So in the step 1, we add a Hadamard gate to the first qubit. We add it, and then we declare another step, and here we add this C0. You remember this C0 which takes 2 qubits? The first one is the control one, and the other one is target, and it will flip it if the first one is equal to 1. And then we run the program, and we can measure our response. So if we measure the first one, and it happens to be 0, the other one, the other qubit will be 0 as well. And let me show you how the circuit looks like. So 2 qubits, the first one we apply the Hadamard to it, the other one we apply the C0, and where this is the control one and this is the target one. Sorry, this is the control one and this is the target one. And here we measure 50-50. If I run this program thousands of times, look what happened. I can get either 0-0 or I can get either 1 and 1. But I cannot have 0-1 or 1-0. This is how entanglement works. You remember, if you measure 1, the other one should have exactly the same state. You remember the secret and the safe and the example? So there is a demo about this one, which is this one. So imagine that you have a secret, like this one, and you want to open the box. So it takes the classical computer, the size of this tries, or the length of this tries to open it, but not for a quantum computer. If you know how to write the circuit, then it will find it in one try. And this is how the circuit looks like. Let me see. So I found a Python, by the way. This is a very famous algorithm which is on the internet. So I found a Python variation of it. And then I did some translation to Java. And it's working. So we create some kind of 6 qubits, because we have 6, length of this is 6. And then we add an extra one to control the bits and apply some CNATs. And of course, where we have 0, it will always, because Hadamard and Hadamard, if you apply it 2 times, it will cancel the value of it, and it will always be 0. So this one is off, and so on. And the other ones will always have 100 chance being 1. We still have 5 minutes for questions, so I'm done. Thank you.